Um, I'm Liz Schell. I'm a PhD student at the University of Pennsylvania, and today I'm going to be telling you about my degradable molybdenum-based phosphate sensor for soil monitoring and precision agriculture. So fertilizer application, as you know, is a balancing act. The same nutrients that we add to the soil, like nitrogen and phosphorus, to increase the growth and yield of our plants, can run off into our water doesn't really work can run off into our water systems and lead to devastating environmental effects from algal blooms that can lead to decreased oxygen concentrations in the water and an increasing area of our coastal oceans downstream of these agricultural areas can no longer sustain marine life due to these effects. So currently farmers rely on laboratory-based nutrient sensing when they are deciding when and how much fertilizer to apply. And this can be slow and tedious because you need to physically take the soil and send it off-site somewhere to a lab. Because of these constraints, places like United States agricultural extension programs recommend taking one soil sample to cover an area ranging from 0.2 to 1.6 hectares. When you're doing this monitoring. However, nutrient concentrations can vary with higher spatial frequency than this. And so if we could also monitor with higher spatial frequency, we could more easily fine tune our nutrient application and only apply fertilizers to the areas that really need it. And this could reduce the amount of nutrients that just leach out into the environment and also save money for the farmers. So biodegradable soil sensing units could help us with this because you can disperse a bunch of sensors in the field and you don't have to worry about collecting them later or keeping track of them. And so you can just put a lot more out. So this work discusses a degradable phosphate sensor in which we've leveraged a lamination-based fabrication technique that was previously developed in our group due to its simple nature where you don't have to rely on any costly vacuum-based fabrication techniques. So the sensor architecture is a 3-electrode electrochemical sensor where the soil solution in the nearby environment acts as the electrolyte. And molybdenum was chosen as our working electrode because when it's oxidized, the phosphate ions react with that molybdate. And then the series of reactions creates a current. And so then, and this chemistry is also leveraged in some existing phosphate detection technologies. Another reason we chose molybdenum is that it's already been used pretty extensively in degradable electronics. But previous works on electrochemical phosphate sensors rely on traditional reference electrodes like silver chloride or saturated calomel. And we have environmental concerns with releasing silver or mercury ions into the soil. And so because of this, we've gone with a tin counter and pseudoreference electrode. Another benefit of tin is that it's cheaper than these traditional materials like silver, gold, and platinum. And if we're using this for a bulk application, we really care about cutting cost wherever possible. So fabrication-wise, we start by laser cutting the metal foils into strips, and then we align those strips onto a tape, a piece of polyamide tape to hold them equidistant and parallel during the lamination process. And then we've chosen to use polycaprolactone, which is a biodegradable polymer, as the substrate because it has a fairly low melting temperature. And so we can pretty easily heat press a bunch of pellets into a sheet and then laminate our metal foils into that sheet. So because we are using a pseudoreference electrode instead of one of these more stable reference electrodes, we can't use potentiometric measurements to quantify our phosphorus. And so we did find some other works like Ferris 2016 and Janka 2011 that use sweep and pulse-based amperometric measurements when they are quantifying phosphate in other situations that also lack the controlled convection that you would need to do, say, like a chronoamperometry measurement. So we chose to go with linear sweep voltammetry, which is a method in which we linearly sweep the voltage that's applied between the working and reference electrodes. and then we measure the current coming from between the working and counter electrodes. And then you get, when you graph that current over the applied voltage, you get a curve that looks similar to this, with a current peak or plateau that is proportional to the concentration of your analyte. So when we did those tests in a phosphate buffer solution with concentrations of what we expect to be environmentally relevant, so 1 to 500 micromolar, we can see our different sweeps with increasing phosphate concentration, and we get higher currents in our LSB scans. However, we can also see from this graph that there's not very distinct peaks or plateaus. And so then what we have to do is go in and take the derivative of those scans, locate the local minima, and so that will designate where our plateau is, and then we can take the current that was measured at that applied voltage. And then when we extract all of those peaks and graph them over the phosphorus concentration in our buffer solutions, we can see a power function trend with a factor of 0.32. So soil solution, of course, presents a much more complex electrolyte than just buffer solutions. There's other potentially interfering ions and such. So for further sensor verification, we collected soil solutions from aliquots of topsoil local to the southeastern Pennsylvania area, fertilized to different dosages with diammonium phosphate, which is a commonly used phosphorus-heavy fertilizer in agriculture. And then we let those soils sit, and the solution and the soil particles naturally separated. And then we collected those solutions with a syringe. And once we had collected our solutions, we subjected them both to testing with the phosphate sensor and also to a traditional technique that's used in the lab called flow injection analysis. And so now we can see on the right are results of our current extracted current peaks over the soluble reactive phosphorus measured by the FIA in milligrams per liter. And so we can again see that increased phosphorus concentration gives us increased current. However, there's two differences between our measurements in the soil solution and our measurements in the buffer solution. One is that when we go to these higher concentrations that are higher than what we characterized in the buffer solutions, the trend actually starts to look more linear instead of a power function. So we may have entered like a different operating regime here. And another difference is that in our lowest point, which was measured by the FIA to be 1 milligram per liter of soluble reactive phosphorus, if we just straight convert that to micromolars, that's 32 micromolars. However, the current that we measured in the soil solutions is about an order of magnitude higher than what we would expect based on the calibration curve in the buffer solutions. So we need to better understand that. But they are like two different tests. And so these also, like the values on the x-axis in these two graphs don't exactly correspond to each other, and also don't exactly correspond to the phosphate that's available for the sensor to measure. So the phosphate concentration in our buffer solutions that we prepared is entirely composed of inorganic phosphate. And because they were adjusted to a pH of 6.7, that puts us in a transition zone between dihydrogen and monohydrogen phosphate about here. However, the sensor, being molybdenum, can only respond to monohydrogen phosphate. And so it is expected that we would measure a lower current if not all of the phosphate is available for the sensor to see. And then the FIA, on the other hand, measures something slightly different called soluble reactive phosphorus, which we think is mostly composed of inorganic phosphates, but it can also include some other phosphorus bound into other types of molecules. So like we've discussed, the portion of the phosphate ions in a detectable protonation state varies with pH. And so our sensor is, of course, going to be susceptible to pH interference. However, it's been shown in at least one other paper before that if you just measure the pH, you can adjust for that effect in post-processing. An additional potential interfering ion is silicate, which is known to interfere in other types of phosphate measurement techniques that use a similar chemistry. And this does depend on like the ratio of how many silicate to phosphate ions you have. So we have to better understand in our specific application in the agricultural fields what those two like the range of those two concentrations that we're ever going to see is, to determine how relevant of an issue this is. But it's been shown in a paper that you can adjust the pH to a very low value to get silicate interference-free measurements with molybdenum electrodes. So you could envision also an idea where you adjust the pH and then you can solve both of these issues at the same time. So in the current state, the sensors need to be placed in an aqueous environment to work and also combined with a potentiostat to take the reading. There are some areas like the Midwestern United States that use these things called tile drains, which are pipes running below the soil surface to carry drainage water out of the fields. So this could present an area where we could already deploy the sensors, but if we wanted to say put them anywhere in the field directly in the soil, my thought is that we could combine it with some sort of porous packaging that keeps the soil particles away, but gives you like a nicer aqueous environment around the electrodes. So one paper that did this or discussed this was by Jiang in 2018. And so like when the field gets irrigated, you have water flowing through the soil, picking up ions, and then that solution collects around the electrodes, keeping away the soil itself. Another component that we need to create a standalone sensing system is the circuitry to perform the reading, applying our voltage, measuring the current, and then also communicate that data. And so I'm part of a research center called the Internet of Things for Precision Agriculture, or IoT for Ag. And one of our projects is to create such a system. And we're envisioning a hybrid biodegradable system that incorporates sub-millimeter scale traditional silicon ICs to kind of balance your performance and degradability of the overall system. And so the idea is that the majority, all of your larger components, antennas, sensors, batteries, packaging would all degrade completely. And then you're just left with these really tiny ICs that are unpackaged. They're predominantly made of silicon, which is what soil is made of. And they're like not much larger than a grain of sand. So we could see, for example, designing an on-IC potentiostat that takes our measurement, using some sort of technique like RFID to communicate the data with the addition of an RFIC and a degradable antenna. One of my lab mates has already developed a biodegradable zinc air battery that could apply the power that we need. And we're also working on some other sensors that could be incorporated in the future. So then when you have this full system all integrated together, we could see that we can get high spatial resolution information across a field of different soil parameters like nutrient levels and moisture levels. And then we can really fine tune where we put these resources in our agricultural field to reduce the effects on the environment from large scale farming without having to sacrifice on things like yield, which is really important as we have like a growing population. Great, so just want to take a minute to thank my sponsors and colleagues, my center, IoT for Ag, and specifically one of my collaborators, Anne-Marie, who I work pretty closely with. Also my lab MSMA, which is led by Professor Mark Alain, and my lab mate, all of my lab mates, but specifically I'd like to thank Yanghang, Vishal, and Jingwen. And then some of this work was performed in the Singh Center, which is a National Nanotechnology Coordinated Infrastructure Hub that's also funded by the National Science Foundation. So thank you for your attention. I'm happy to take any questions.